Welcome students, welcome to our series of lectures in material science. In the previous videos, we have seen what types of crystal systems, how many types of crystal systems. Okay, we have studied about cubic structures, in which we have studied about one atom based structures and two atom based structures like CSIR, NaCl, diamonds. Okay, the diamond structure is very important from exam point of view also, I told. Okay, now we'll get a doubt here. Some of you might be getting a doubt. Atoms cannot be seen with our naked eyes. Not only now, never. Okay, we cannot even see atoms with any powerful compound microscope. Also, atoms cannot be seen. Then, how we are able to tell that in diamond the structure is like this, right? In NaCl, Na plus is here, Cl minus is here, like that. How do we people know all these things? Okay, you may be getting a doubt when something I cannot see, right? Microscopically inside, how the atom structure we are able to tell. Okay, that the technique is what is known as X-ray diffraction. Okay, the crystal structures can be understood by a process called diffraction of X-rays. Okay, what is diffraction? You must have studied in your 10 plus 2 level, that the light, bending of light around an obstacle. Okay, right? Then, but there is one important point which we have to remember. What is diffraction means? Okay, suppose say light always travels in straight line, that everybody knows. Right, the rectilinear propagation of light, we say light always travels in straight lines. Okay, right. Now suppose if I put one obstacle here, okay, if I put one obstacle here, in general if it is our window or a door or any hole of a macroscopic size, even up to 1 millimeter size hole also, right, with an alpin, if you make one hole in the paper and send light goes like this and falls like a patch here. Okay, but when the size of the hole is extremely small, remember extremely small, how small it should be, right? The size of the hole should be comparable to wavelength of light. Okay, right? Comparable to wavelength of light. Wavelength of visible light is how much? Is around 4,000 angstroms to 7,000 angstroms. On an average, I'll take 5,000 angstroms. Okay, if the size of the obstacle, that pinhole size is comparable to 5,000, it not be equal to 5,000, maybe 2 times more, 3 times more, 4 times more, like that. That's known as comparable. Okay, when the size of the obstacle is comparable to wavelength of light deviates from its rectilinear path. Okay, light bends, we say. Bending means it's not like bends and it won't go like that. Okay, that's not bending. Okay, it is not this bending. Light deviates from its rectilinear path and again travels in another straight line path like this. Okay, this bending of light around an obstacle of size comparable to wavelength of light, that word should be used. Okay, right? This is known as diffraction. Means instead of going straight, right, it goes in direction like this, and it goes in direction like this and like this also. Okay, this property of light is known as diffraction. Okay, light has how many properties? Light always travels in straight lines, rectilinear propagation. Light undergoes reflection, light undergoes refraction, interference of light, diffraction of light, polarization. There are 6 properties. This is what is known as diffraction. Okay, this is what is known as diffraction. Okay, right? The only thing for diffraction is, the only critical point which you have to remember in diffraction is the size of the obstacle should be comparable to wavelength of light. Then only we can observe diffraction. So, is it possible to observe diffraction of light in our visible light? No. In our daily routine? No. Okay, because we cannot have that small, comparable to wavelength of light obstacles, we don't create. The light won't diffract when it is passing through your window or when it is passing through any ventilator hole. No. Okay, right? Now, so when I make the small, the wavelength of light, the size of the obstacle smaller and smaller and smaller, the deviation will keep on increasing. We'll be getting more and more deviations like this. Okay, this is called 0th order diffraction. Okay, it has not undergone diffraction. That part of light has gone straight only. Only a small fraction of light is getting deviated and going like this. This is called first order diffraction. Okay, first deviation from its rectilinear path is known as first order diffraction. Okay, these two are called second order diffraction pattern. Okay, second order diffraction. Third order, like that. Okay, how many orders are observed? How many orders will come? How much will be this deviation? Depends on the size of the obstacle and wavelength of light. The smaller the size of the obstacle, the greater will be the deviation and more diffraction orders will be observed. Okay, that's why in order to observe diffraction with light, people use something known as optical gratings, where with an extremely fine diamond point, okay, people draw some 15,000 lines per inch. Okay, that is 1 inch is 2.54 centimeters. Per inch, they draw 15,000 lines. They are called students' gratings. Okay, such that if you calculate the distance between two lines, right, the distance between two lines, right, it will be around 15,000 to 16,000 angstroms. Whereas I am using light of wavelength around 5,896 or 6,000 angstroms. That is, it is 2, 2.5, 3 times more, okay, comparable to wavelength of that light. Okay, you can observe the diffraction. We can observe diffraction. Okay, so visible light diffraction is observed with optical gratings. Optical gratings where people draw, okay, extremely fine lines on some organic chemical substance. Okay, they will take negatives of that, etc. They will be put into thin glass plates. Okay, the distance between any two lines, right, is of the order of around 15,000, 16,000 angstroms, comparable to the wavelength of 6,000 angstroms of light I am using. So I can observe diffraction. Okay, no problem. But what are X-rays? We have seen in the beginning introduction class only. What are X-rays means? X-ray wavelengths are roughly from 0.1 angstroms to 0.1 angstroms to roughly about 100 angstroms. Or even just in what you call 100 angstroms are used in diagnostics. Okay, 200, 300 angstroms. Usually in physics we use 0.1 angstroms to roughly about 10 angstroms. Okay, now I want to observe diffraction with X-rays of this wavelength range. Okay, X-rays means this wavelength range. Now I want to observe diffraction with X-rays like this. Okay, of this wavelength range. Now optical gratings have 16,000, 17,000 what you call angstroms separation between two lines. Okay, and when I use 1 angstrom wavelength X-ray beam, 1 angstrom is not comparable to 16,000, isn't it? Comparison means 2 times, 3 times, 4 times it should be. You cannot compare 1 with 16,000. Okay, they are in the ratio 1 is to 16,000. Nobody says 1 is to 2, 1 is to 4, 1 is to 5. That's all. Okay. So, right, just like our normal room window is very big compared to wavelength of visible light, we don't observe diffraction. For X-rays of 0.1, 0.2, 1 angstroms, even these optical gratings with 16,000 angstroms become very big. So diffraction will not occur. Diffraction will not occur with optical gratings. Okay. Now I want to observe diffraction with X-rays. How is that possible? Okay, means what? Now I should create a grating where the distance between two lines should be of the order of X-rays. Means 1 angstrom means the distance between two lines should be 3 angstroms, 4 angstroms, 5 angstroms. 16,000 angstrom drawing itself is very difficult. Okay, we'll have gratings of 15,000 lines per inch, 25,000 lines per inch. Now with the laser beams, 40,000 lines per inch are also coming. Okay, but still that is not sufficient. I have to draw lines so close that the distance between them is 4 angstroms, 3 angstroms, like that. Is it possible? Impossible mechanically. Okay, but forget about now, 2021. Okay, imagine 1921. Okay, 100 years back when people were studying the structures of scientists were studying crystal structures, there were no laser beams in those days. There were no such highly technical sophisticated equipment. Okay, then how did they observe diffraction with X-rays? Means a scientist called Laue, L-A-U-E. Okay, scientist called Laue suggested that crystals themselves can be used as grating elements for X-rays, he said. Okay, a very beautiful idea for him. He got that very beautiful idea, right? Because we have seen CSCl and NaCl, the distance between two atoms is about 2 angstroms, 3 angstroms, 4 angstroms. And atoms are arranged in a very systematic manner like this. And atoms are arranged in a very systematic manner like this. Okay, distance between any two atoms, if you see, it's about 3, 4, 5, 6 angstroms only. That is comparable to the wavelength of X-rays, and atoms are in a very systematic arrangement. Okay, means I can imagine that this is a line. Okay, imaginary line drawn by nature itself. Where, okay, this is another plane of atoms. This is another plane of atoms. This is another plane of atoms. This is another imaginary plane of atoms. Right, now this plane of atoms behaves like the line I have drawn in the optical grating with a fine diamond point or with like a laser beam. Okay, right. So he said that these can be atomic planes can be considered as the lines drawn. Okay, atoms can be atomic lines. Right, the distance between two atoms or two atomic planes is of the order of wavelength of X-rays. Okay, right. So this is crystal. The only difference between this is also grating element, he said. This grating element and optical grating, what is the difference between these two? Optical grating is in the form of a thin glass plate. Okay, it is in the form of a thin glass plate. It is a two-dimensional entity. Whereas crystals are three-dimensional. Crystals are three-dimensional. So, these crystals are known as 3D or space gratings, we call. 3D or space gratings. Okay, 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 3D or space gratings Okay, three-dimensional or space gratings. Okay, because this imaginary atom, see, nobody has drawn any planes. Okay, right? Atoms are like that. I imagine this is one plane of atoms. I imagine this is another plane of atoms. This is one imaginary line. This is another imaginary line where the atoms themselves will act as diffraction centers. Atoms here, they act as diffraction centers. They diffract X-rays from their rectilinear path, and what you call, they make X-rays undergo diffraction. Okay, so crystals can be used as three-dimensional or space gratings in order to observe diffraction with X-rays was the idea proposed by a scientist called Leavitt. Okay, right? Now, here the atoms themselves act as diffraction centers. From the way the X-rays get diffracted, right, we can understand the position, distribution of atoms and their structure. How they are arranged, right, in space can be understood using this X-ray diffraction. So, in the examinations, you will find crystal structure can be analyzed using which type of rays. Okay, yeah, visible light, infrared light, X-rays, UV light, like that. Okay, they can be observed with X-rays. Remember, because atomic size are about 1 angstrom, 2 angstrom, 3 angstroms. Okay, something that atom should act as a diffraction center, and diffract X-rays means, okay, wavelength smaller than that. See, any wave should get diffracted or scattered means the size of the object must be greater than the wavelength of light used. Okay, because see, light is falling on me and entering into your eyes, you are able to see me because my size is greater than the wavelength of light. Okay, wavelength of light is 5000 angstroms. Means with visible light, what size objects we can see? At the most 3000, 4000 angstrom or 5000 angstrom size only we can see. Even with a microscope also. Because light should get scattered, isn't it? For proper scattering to take place, the size of the object should be greater than the wavelength of light incident. Okay. Right, our wavelength of visible light is around 4000 angstroms. Okay, the bacteria size, we can see bacteria under a microscope. Why bacteria size is greater than 5000, it's around 10 20, 30,000. So, when light falls on bacteria, it gets what you call scattered, and I can see bacteria. But we cannot see virus with a microscope because size of the virus is smaller than the size of the wavelength of visible light. Okay, so virus cannot be studied using normal compound microscopes. Okay. Similarly, atoms cannot be seen. Atoms should be seen means have to use X-rays only. Okay, have to use X-rays only because only X-rays get scattered from, not even what you call UV light. Forget about visible light. Not even UV light gets scattered from what you call atoms. Only X-rays can get scattered from atoms. Okay, and that X-rays are not visible to our human being. When X-ray enters into our eye, damages our eye, it won't give us vision, isn't it? It will make us lose our vision. Okay, so we can never expect to see atoms with our naked, what you call eye or what you call any microscope or something like that. Then how people are able to give pictures of atoms that IBM has given iron atom structure. One photograph, famous photograph is there. It is nothing but computerized positions of atoms drawn in three-dimensional space. That's all. Okay, it is not that I can see the atom personally. Okay, right? The scanning tunneling microscope or AFMs, etc. Some highly advanced instruments. They will locate the positions of atoms. Okay, here one atom is there, here one atom is there. That a computer gives a three-dimensional picture. Okay, develops a three-dimensional structure. Okay, so the point here is, right, how do we, what you call, study the structures of crystals? We have to use X-rays. What phenomena of X-rays is, diffraction of X-rays is useful, right, in studying the structures of crystals. Okay, so one important law regarding X-ray diffraction is known as Bragg's law. Okay. Bragg's law gives a relation between the atomic distances and the wavelength of light used in the order of diffraction. Okay, now consider a crystal plane like this. Okay, a crystal like this where atoms are arranged in some systematic manner. It can be cubic or anything. Okay, so atoms are like this. This is one imaginary plane of atoms. Okay, this is another plane of atoms like this. These are called successive parallel atomic planes. These are called successive parallel atomic planes. Okay, because it is a regular periodic structure, distance between these planes, distance between these two planes is called interplanar distance. It is called interplanar distance. Okay, it is called interplanar distance. Okay, so distance between any two parallel planes will be same, d only. Okay. Now what do I do? We will send an X-ray beam, monochromatic X-ray beam of wavelength lambda like this. Monochromatic single wavelength. Okay. X-ray beam of wavelength lambda like this that comes and falls on this atomic plane and gets diffracted or reflected, whatever you call it. Okay, like this. Okay, right? It gets diffracted or reflected like this. Right? From the crystal, it is getting diffracted means from whom it is getting diffracted actually, right? How? From atoms only. Okay, microscopically, see, we see this as a pen, but microscopically, when I said an X-ray beam does not see this like a pen. Okay, it sees in terms of atoms only because its atoms are comparable to its size. Okay, so we don't see what you call the at microscopic level, it is not the pen, it is the atoms which will reflect or diffract or whatever it is. Okay, the rays which are incident on them. Okay, so this is a monochromatic X-ray beam of wavelength. I will call this as incident light PQ. This Q is one atom. Okay, PQ incident ray comes and falls and gets diffracted and goes as R, QR. QR. Another ray in the beam gets diffracted or reflected from another atom in some other atomic plane and gets diffracted like this. I'll call this second beam. It's also the same wavelength lambda only. I'll call this as P dash, this atom as Q dash, and this as R dash. So PQR and P dash, Q dash, R dash are two X-ray beams, right, which got diffracted from successive parallel atomic planes. Okay, right now this angle is known as what you call glancing angle or screening angle or Bragg angle theta. Okay, means the angle made by the X-ray beam with the atomic plane directly is known as glancing angle or Bragg angle. Okay, now Bragg's law says what? Bragg's law says that if the path difference between these two rays, PQR and P dash, Q dash, R dash, the path difference between these two rays is an integral multiple of lambda. Okay, that is if it is equal to n lambda, where n equal to 1, 2, 3, etc. What you call n equal to 1, 2, 3, etc. Okay, then what you call constructive interference takes place, and right, we'll get maximum intensity. Whenever there is constructive interference means in waves, imagine, you know, waves have crests and troughs like this. This is known as a crest, this is known as a trough. Okay, when crest falls on crest, intensity or amplitude becomes maximum. Trough falls on trough, trough's amplitude will increase. Okay, that's known as constructive interference, we'll get maximum intensity. Okay, if crest falls on trough, crest is like this, go trough will be like this. If crest and trough fall on each other, they nullify or neutralize each other. Intensity will become minimum or sometimes zero also. Okay, right? So constructive interference should take place and we should get maximum intensity. What did he say? The path difference between these two rays, must be equal to n lambda, where n equal to 1, 2, 3, etc. n equal to 1, 2, 3, etc. It is called order of diffraction. Order of diffraction. If I say n equal to 1, it is called first order diffraction. Okay, n equal to 2, second order diffraction, like that. Okay, right now, what is this path difference? Name itself says difference in the distances traveled, path. Okay, first ray has traveled. What is the path? Suppose say I start from this point and go to some other point which is at 5 kilometers, or say some distance. I will take a route where I have walked around 5 kilometers. Okay, my friend here sitting behind the camera, right? He starts from the same point and goes to the same point, but he chooses a path where the distance traveled by is 6 kilometers. Okay, both of us are starting from the same point, both of us are reaching the same point, but I have taken a path which is around 5 kilometers long, that path, whatever it is, and he has taken a path which is about 6 kilometers. What is the path difference between we two? Okay, means it is 1 kilometer, because he has traveled 1 kilometer extra distance in order to reach the same point. That is known as path difference. Okay, so what is the path difference means? PQR is traveling some distance, P dash, Q dash, R dash is traveling some distance. What is the extra distance traveled by one ray compared to the other ray? By looking at the picture itself, you'll understand, right? Second ray is traveling more distance than first ray. What is the extra distance? That extra distance should be, that is known as path difference. Okay, that if it is equal to 1 lambda or 2 lambda or 3 lambda, we'll get maximum intensity, otherwise minimum intensity. As simple as that. Okay. Now, how do I calculate the extra distance traveled by second ray compared to first ray means? Now say both of them are starting from the same point. Okay, both of them are starting from same point. Now, both of them are traveling parallelly like this. Up to this point, both rays have traveled. Okay, both rays have traveled same distance. There is no path difference between them. Up to what point? Up to this point. I will draw a normal like this. I will put a point M here. QM is a normal drawn from Q on to the second beam. Up to that QM, both rays are traveling same distance. Okay. Now the second ray is traveling the extra distance of MQ dash. First ray is getting diffracted from Q only, whereas second ray is getting diffracted from Q dash. So the extra distance traveled by the second ray compared to first ray before diffraction is MQ dash. Again, now look here, it is getting diffracted and going straight like that, but it is traveling some extra distance and getting diffracted from this atom Q dash. Now in order to catch up with the first ray, right, it has to travel some extra distance like this. Now again, from this point onwards, both the rays are traveling the same distance, the path difference between them will be 0 from here onwards. But in order to catch up with the first ray, what is the extra distance that traveled by the second ray? Means, right, I will draw one more normal from Q on to this second ray, Q dash R dash, I will denote it by N. Okay, so the second ray has to travel an extra distance of Q dash N compared to first ray in order to catch up with it. Rest of the journey is both of them are traveling same distance, the path difference is 0. Now, what is the net extra distance traveled by second ray compared to first ray means it is this MQ dash plus Q dash N. MQ dash plus Q dash N is the path difference. Path difference. MQ dash plus Q dash N. Okay. Now from geometry, I have to calculate what is this MQ dash and Q dash N in terms of interplanar distances, etc. Okay, now if this angle is theta, now I will draw one line Q dash. Q dash is nothing but interplanar distance D. And this is a right angle triangle because this is a normal drawn, this angle is 90 degrees. If this angle is theta, your 10 plus 2 or 10th class geometry, okay, refer that. This angle also becomes theta, this angle also becomes theta. Okay, now from this triangle MQ dash, it is a right angle triangle. What is sin theta equal to? What is sin theta equal to? Sin theta equal to opposite side of the hypotenuse, that is MQ dash by, right, what hypotenuse is nothing but Q dash. Hypotenuse is nothing but Q dash. Right, so what is MQ dash equal to? MQ dash equal to Q dash into sin theta. What is this Q dash? Q dash nothing but our interplanar distance, isn't it? So Q dash nothing but D, so this is nothing but D sin theta. So MQ dash is equal to D sin theta. Similarly, from this triangle Q dash, again sin theta, if I take sin theta equal to opposite side, okay, Q dash N, sin theta equal to Q dash N by, again hypotenuse is Q dash. Q dash nothing but D only. Okay, D. So therefore, Q dash N is also equal to D sin theta. Okay. So MQ dash plus Q dash N. MQ dash is D sin theta. Q dash N is also D sin theta. Therefore, MQ dash plus Q dash is nothing but D sin theta plus D sin theta is nothing but 2D sin theta. Okay, this is the path difference, right, between these two rays. Bragg's condition, Bragg's law simply says what? If this 2D sin theta is an integral multiple of lambda, that is n lambda, okay, right, constructive interference takes place. That is, crust falls on crust, trough falls on trough, and we get maximum intensity. Otherwise, we get minimum intensity. As simple as that. Okay. So this is our Bragg's law. Okay, of course, so we can expect one or two problems also. Right? It is this Bragg's law which is very, very fundamental in X-ray diffraction. Okay. Here we have to understand the terms here. Okay. What is this D? D is known as interplanar distance. Distance between these two atomic planes. Okay. Right? And what is theta? Theta is known as Bragg angle or glancing angle or screening angle. Let us call it as Bragg angle. Okay. Right? The angle made by the X-ray beam directly with the atomic plane under consideration. That is known as theta. Okay. These two are parallel rays, isn't it? If this makes theta, this also makes theta. Right? And what is this n? N is called order of diffraction. N is equal to 1, 2, 3, etc. etc. What is wavelength? Lambda. Lambda is the wavelength of the X-rays used. Monochromatic X-ray beam we should use. Okay. Right? In single wavelength X-ray beam. That wavelength of the X-rays is lambda. N is known as order of diffraction. Theta is called Bragg angle or glancing angle. Right? And B is known as interplanar distance. Okay. Remember this term. Okay. I have to. Right? Memorize this point. Interplanar distance, Bragg angle, order of diffraction, wavelength. This is 2D sin theta equal to L lambda is called Bragg's law. Very, very crucial. The first step in understanding the structures of crystals. Okay. Right? We can expect some problems also. Right? He will give you what you call B and theta. He'll ask you what is the order of diffraction. Or he will give you N lambda and theta. He'll ask you what is interplanar distance, etc. etc. Now, here, that manipulation part that we can see later on. Okay. Now, my interest is somewhat deeper. Now you may get it out, sir, why have you taken atomic planes like this only? Okay, because it is a three-dimensional space. I can consider planes like this or like this or like this or like this also, no, isn't it? Sir, I will take my atomic planes. Somebody comes and says, sir, I'll take my atomic planes like this. Yes, you can take, no objection. Only thing is, if the interplanar distance with these two atomic planes, if it is d, right, it may not be equal to d, it may be some d1. The interplanar distance between such atomic planes, these are also atomic planes only. Or one student may come and say that, sir, I will take the atoms like this. Yes, he is free to take. Okay, you can take atomic planes like this also. These are also atomic planes only. Only thing is, the distance between two atomic planes here may be d2. Okay, you can take it in any direction like this. It is purely our choice. It is purely our choice. Here the interplanar distance may be d3. Okay, like this. So if I do an experiment with these planes, I'll use d1. I'll use interplanar distance as d. If you do with these planes, right, your interplanar atomic distance will be d3 like that. Okay. Now the question is, I did an experiment using these planes. I did an experiment using these planes. Now, I'll give you the crystalline. I want to tell you, you also do the experiment using these planes only and verify my result. Means I should be able to tell you that I have used so and so planes, so you also use so and so planes only. Means you should, the moment I say so and so planes, means you should understand that sir has used these planes, so I should also use those planes only and verify. Means these planes should have some nomenclature, isn't it? Some name, some address, some identity they should have, isn't it? If I say so and so planes, you should be able to understand. Means what? All these planes should have one name or some identity, like a pin code or a house number, door number or name, something like that. Okay, these planes should have another identity. These planes should have another identity. Means the planes, the imaginary planes in the crystal, three-dimensional crystal, anybody can visualize any parallel atomic planes, but every atomic plane should be given some identity, some name, some door number, some address, some Aadhaar card, something like that. Okay, and who gave that identity to the crystal planes, atomic planes in the crystals? Means a scientist called Miller. Okay, this is exam point of view important in material science, one gunshot question in electrical or ECE. Okay. Right, on Miller indices, right? So a scientist called Miller has used a set of three integers, H, K, L. You can put commas in between them or you can avoid commas, okay, whatever it is. H, K, L, small letters, a set of three integers to designate a given set of parallel atomic planes. Miller indices, they do not talk about an individual atomic plane. Remember, all planes parallel to that plane will have same Miller indices. Because I am interested in that orientation, not in one particular plane. How many planes will be there? Billions of planes will be there. Okay, just like a huge function hall which is having 2000 chairs. Okay, right? I am standing here. I will count what you call the rows from here. You are standing there. You will count your rows from there. So which row is immaterial? All are chairs, rows of chairs only. Okay, it's a very huge, what you call, say, half kilometer long function hall, which is having 1000 rows of chairs. Okay, I am standing here. I'll call this as my first row, this is second row, this is third row. You are standing there, right, near 100 meters away from me. You will count your chair rows, you will call yours as first row, second row, like that. This is also one row of chairs only. That is also one row of chairs only. Same is the case. There is no spin. All that what is important is they are all parallel to each other. If crystal is big, okay. We have seen beginning only 10 to the power 23 atoms will be there. Billions of atomic planes will be like. So which plane? If you are here, you will start from here. If you are there, your plane is like that. Only thing is what? Your plane and my plane are parallel to each other. So both are talking about same planes. Okay, so Miller indices, they do not indicate a single plane, they indicate a set of parallel planes in the crystal. Okay, all parallel planes in the crystal will have one particular set of Miller indices. Okay, now if I say, right, use 100 planes in so and so, right, NaCl crystal and do the experiment. The student who is familiar with this Miller indices will understand that I am talking about so and so plane. So we'll use so and those planes only and we'll do the experiment. Or sometimes I'll say use 2, 3, 1 planes and verify this result. You will understand immediately that what planes I am talking about. Yes, sir is talking about these planes. So we should use these planes only. So Miller indices, Miller has given an identity, a name, an Aadhaar card, okay, a self-identity for every set of parallel planes, not for individual plane. Remember, that also is a question which has got repeated, which keeps on getting repeated. Miller indices, they indicate a particular plane, a set of perpendicular planes, a set of parallel planes. Okay, it can indicate any plane, something like that. Some 4 options will be given. Miller indices indicate a set of parallel atomic planes. Okay, right? They are denoted by HKL. Okay, these Miller indices are important from the exam point of view. How to evaluate, how to get these Miller indices. Okay, that we will cover in the next video. Okay, thank you for today.